Hello everyone, this is Shilei from AMD. Today I'm going to talk about extending ThinLTO support for AMD GPU. If we have a GPU program that has multiple source files, there are two compilation modes here, or two ways to compile it. The first one is just the default compilation. At compile time, the compiler basically compiles the source file all the way to the binary code, or we call a device image. And then if we have n device image, and now we just eventually have n device images. Unlike a CPU program, in this mode, for AMD GPU, there cannot be any interaction between those translation units. By interaction, I mean there cannot be any external function call or some cross-translation unit global variable accesses. That is because a GPU program is very resource sensitive. So when the backend compiles the kernel, it needs to know exactly how many resources the kernel is going to require, which all include all the functions that might be reachable from the kernel. Now we have the GPU RDC mode, and in this mode, at compile time, the compiler just compiles the source file to IR, and at link time, all the device IRs will be linked together into a single IR, and that single IR will go through the middle end and the back end, and eventually we will only have one device image. So this is effectively the full LTO compilation. And in this approach, all the cross-translation unit function calls and global variable accesses are resolved at link time. But since it is full LTO, it also has the drawbacks of LTO. So the single IR can become performance bottleneck easily if it is very large, which can easily happen when there are so many source files. That is because the entire middle end and back end just run in serial, so which is not ideal. So we have come up with some solutions to speed up the compilation, and one is module split. Here I'm going to use this call graph to demonstrate the idea. We have some circles here representing the functions, and we have some arrows representing the function call. This call graph can be split into three strongly connected components, or SCCs. And since each SCC is self-contained, we can just run the compiler or the middle end and back end in parallel to finish the compilation. This can work most of the time, can significantly improve the performance, but it also has some drawbacks. First, if the call graph ended up just with one SCC, it won't help. And the split actually happens quite late in the middle end, so almost all the middle end is actually running in serial. And lastly, it also doesn't work with compiler cache. So a minor code change can lead or can cause the entire GPU program to be recompiled. So we definitely want to explore more options. And the ThinLTO can be a quite promising solution here. However, it cannot work out of the box for AMD GPU. So I'm going to use this example to demonstrate the reason. We have a couple of boxes here. They represent translation units. And we have some white arrows represent function calls within a translation unit. And we also have blue arrows representing the external function call. We have some yellow circles representing the kernel functions, which serve as the entry point of a GPU program, and the red circles just the regular device functions. So in ThinLTO, only the module summary are merged at link time, and the actual module still gonna run still gonna go through the middle and the back end individually. So like the limitation I mentioned earlier, we still need to resolve those external function calls. One of the key steps of ThinLTO is function import, which was originally designed to import functions from one module to another when inlining them would be beneficial. But here we take advantage of that by forcibly importing all the callees of the external function call. And after the import, each translation unit become self-contained such that we can just compile them correctly. Another thing to note here is after the import, the last two modules actually become useless because everything in the module have already been imported by the other two. So compiling them is just a waste of time and resource. In AMD GPU, we enable the internalized path, which gonna internalize as many symbols as possible. After the internalization, basically the last two modules become empty, and we're not gonna compile it. So the function import can work most of the time, but it cannot work with one last case, which is the indirect function call. So I slightly modify the example here. So the dotted arrows represent indirect function call, and the purple circles here just represent the potential callees. The module summary does not and cannot have information about the potential callee, so the function import doesn't import anything for indirect function call. Before I talk about the detail, the solution for that, I'm going to quickly go through the current status of ThinLTO support for AMD GPU. So most of the things should work with the latest LLVM trunk, but if the code has indirect function call any form of it, including C++ virtual function, it may or may not work. The tricky part here is the compiler is not going to give you any warning or error, probably not going to give you anything. So even if it is compiled correctly, successfully, it doesn't necessarily mean it can work. And even if it does, well, it just happens by chance. So the solution for that is to have the two-round compilation. In the first round, each module checks whether it has any functions whose addresses are taken. If it doesn't have any, then it's going to skip this round. And here we have two modules they have functions whose addresses are taken. And then we are going to clone the module and use the clone for the rest of this round. When we clone the module, we start with those functions whose addresses are taken and recursively include all the functions that will be reached by them. So here it looks like we are cloning the entire two modules, but it is not necessarily the case for the other. After the cloning, each module just going to go through the regular ThinLTO pipeline, including the function import if necessary. So the compilation here will be in parallel. And after that, we will get some temporary code object files, which also include all the necessary resource usage metadata. And we are going to merge the resource metadata and finish the first round. In the second round, we run the ThinLTO pipeline again, but this time with the merged metadata. If a module has an indirect function call, the backend is going to look up the merged metadata and determine the resource usage of the potential callee. The lookup here is based on function signature, so we assume that all the functions with the same time can be the potential callee of the indirect function call. We understand this is conservative, but it is still guaranteed the correctness. So this is still working in progress, and in fact, LLVM already had some two-round ThinLTO compilation in the trunk already. So for function outlining for the host code, and we also believe that what we are proposing here can be also extended for other purposes. For example, if we have a really large function, they can just be compiled in the first round and then skipped in the second round. And it can also be beneficial for other targets that may not have similar ABI rules as AMD GPU. So yeah, that is all. If anyone is interested in the implementation detail, feel free to talk to me. Thank you.